project led by the Prince William Sound Science Center. Our partners include the UAF Alaska Sea Grant Extension Office, the North Chapter of the Prince William Sound Audubon Society, who hosts one lecture a month, and the Forest Service, who generously donates the building and equipment. Succeeding. My name is Meadow. I run the lecture series for the Science Center and also other educational programming. If anyone has any ideas for lecture topics or speakers, please let me know. I'm always interested. Next week we will have Paula Cullenberg presenting on the graying of the fleet, a closer look at our fisheries next generation. It should be a real interesting talk. There's going to be a sign-in sheet going around. If you already signed in, obviously you don't need to again, but please do pass it on so that we can get a full number of how many people attend the event. Now I'd like to introduce the Science Center's very own Rob Campbell. Yay!
Thanks everybody for coming out. I didn't think anybody would be here. I don't know if I would have left the house.
So nice out.
Yeah.
You live at the end of the dock.
That's true. I have a quarter mile of sideways rain to navigate. I am downsloping on a cold, so I'm hoping my voice will last, and I drank about a gallon of tea today, so there may be an intermission while I have a pee break. We'll go with it. Yeah, I'm just going to talk a little bit about Prince William Sound and the state of the oceanography in the grand scheme of things. So let's back up a little bit and situate ourselves.
Do you want me to hit the links?
Can we do those a little bit?
I can do this, or I can do, let's see, this.
That's nice.
Good.
You want them all off?
Oh, turn them all off.
Well, he's got a couple of tricks up his sleeve. I just want to make
Oh
sure.
yeah.
Let me know when you want to break up a trick.
Right. So we're right here in Cordova. And here is the Gulf Coast. And the reason I show this is to show this great band of water along the coast that really drives our oceanography. Perhaps you've noticed we get a lot of rain, and there's also all these ice sheets along here that are grinding away at the rock and creating this turquoise-colored water. And that's the Alaska coastal current. It travels up from DC under the rain. It comes up and it kicks in Elias here and kind of whips around like a fire hose. Sometimes it travels along the shelf, sometimes it seems to head towards the sound. There's our Copper River right there with a nice plume, and again, that's traveling along the coast. Physics aren't too important. And then in the Prince William Sound proper here. And really what's driving this, and I'll bring this up a few times today, is the tendency of water to form layers. Can you hit the link? So what I've done here, some of you will have seen this before, I just took a little bit of regular old table salt and mixed it up with some red food coloring and put some salty water on the top, which is the dark red, and then just poured some fresh water on top. I can't really think of a better way to show how water tends to layer up than to let you look at it yourself. It's remarkably stable. This is actually driven by the density of the water. By adding the salt, I'm adding weight, which changes the density. So it makes this water at the bottom kind of heavier, and then the water on top has no salt in it, so it's less dense, it's lighter, and it tends to float up on top. And that's really what's driving the Alaska coastal current here. All of that fresh water is running off the mountains and into the ocean, which is salty, and it's riding up on top of it. It gets pinned against the coast by the Coriolis force, but we won't worry about that. Can you kill those lights again? Pretty dynamic place. Everyone's probably aware in Alaska in general we're in kind of a warming trend. These are just some temperature records I got from the closest places I could find. This is Valdez on the top and Yakutat on the bottom, and it's even in Fahrenheit. From 50s till present, we have a pretty clear warming trend in the atmosphere.
What happened there in the 60s, though?
That's a good question.
Fish on the bottom.
As well, some of you have probably heard about the blob. It's received a little bit of press. This is the temperature anomaly of the North Pacific for the winter of 2014. we had this really weird anomalous warming event that happened right out in the Gulf that people have been talking about quite a bit. There's been quite a lot of effects noted, like seabird die-offs, red hides and toxic algal blooms, changes in food webs that are killing seals and things like that. Here it is last year, so it had moved inshore a little bit, but still quite a big pool of really warm water. And the interesting thing is this actually isn't global warming. This turns out, according to the state of the art, it'll probably change. But it was really a lack of cooling that created this warm anomaly. Normally in the winter, perhaps you've noticed, it's a little stormy, things tend to get mixed up quite well. But for some reason, and the atmospheric scientists are still working on it, there was a very long, prolonged high-pressure system with not a lot of storm systems moving through, which really dropped down on mixing it. So, the axis here is temperature. You can think of it as cooling. And this is just a time series from 1980 till 2014. And blue here is advection, so this is just cooling due to water moving around in the North Pacific. And it was basically zero, so very little advection. The surface fluxes are mixing at the surface, things like storms mixing in cold air to the water, cooling down the surface. And then entrainment is actually the opposite of that. It's mixing on the bottom. So going back to our two-layer demo, that would actually be mixing from underneath, from ocean tides and things like that. And so that all is sort of summed up by this mixed layer temperature change here. So this is what you might usually expect, a cooling over the winter of something like 7 or 8 degrees Celsius averaged over the area. But for whatever reason, in 2014, it just didn't cool. So we were left with this warm anomaly. As well, all of that ice mass ringing the margin of the Gulf of Alaska is melting. This is a time series of ice mass. It's actually measured from satellites. If you have two satellites and you measure the distance between them very, very precisely, you can actually map the gravity field of the Earth. And from that, you can infer how much water and ice is actually overlying it. And so that's what this is. This is just mass balance of ice ringing the Gulf of Alaska. And so we see this sort of seasonal cycle, like you'd expect, winter, spring, rain, thawing, and all of that, but a clear negative trend. And if you don't like graphs, I can show it to you as well. This is a landside image of Columbia Glacier up around the corner from Valdez. This picture was taken in 1987, and here it is last year. It's a pretty unmistakable thing to see. In 25, 30 years, it's receded about 20 kilometers. It's been losing something like 20 billion tons of ice every year. Just this glacier between 97 and 2008, the amount of ice it lost is responsible for a 1% rise in sea level worldwide. So big numbers, large amounts of ice that are disappearing.
1%, you said?
1%. So, to plug Science Center programs, for the last 5 years we've been doing regular trips around the Sound. This has been funded by the Exxon Valdez Oil Spill Trustee Council. They have a program called Gulf Watch Alaska. It's gulfwatch.org if you're interested. It's a cast of thousands working in the Sound, Cook Inlet, out on the shelf, Kodiak, all over the place. But at the Science Center, we've been doing a regular circuit of the Sound. So we go out in the Science Center research vessel and turn fuel into noise. And at each of these stations, our basic measurement that we do is called a CTD cast, and that stands for conductivity, temperature, and depth. And that's this little guy right here. It's just a self-contained instrument. We turn it on and start measuring temperature and conductivity, which tells us about the salinity of the seawater. And it's got a little pressure transducer on it that tells us how deep it was. So that gives us a record of temperature and salinity from the surface to about the bottom. So we drop that off all in one place. It's a pretty simple and cheap measurement technique. Now, of course, we've really only been doing this since 2010, which is a pretty good data record. We've done this trip something like 50 times since we began in late 2009 and have a pretty good database built up just from that. But to really put this into context needs much longer time series. So I've spent quite a lot of time combing the internet, various databases, to pull down all the CTD data I could basically get my hands on. So as well as what we've been doing, I went and got things from University of Alaska Fairbanks, NOAA, wherever I could get it. And this is just a map of where all those CTD casts were taken. And you can see at the top there, it's a bit over 23,000 individual casts and currently at about 6.6 million individual data points. So it's a pretty big data set at this point, and we're adding to it continually. And for the purpose of this talk, I've divvied it up into three areas. And the ones I'm really going to focus on are the Central Sound here in blue and the Northwest Sound in yellow. This is kind of center of the sound. It has its own little circulation. Often there's a little feature in the middle that has the water spinning in it. And in the Northwest Sound, of course, is where all the glaciers are. And this is mostly a matchup with some other researchers who have looked at it in a similar way. Just to give you an idea of how much data there is, this is just showing those four areas, and here's the Central Sound here. This is time along the left-hand side here, so starting at about 1975 and going to September 27th of this year. And this is just the day of the year along the bottom, so just to give you an idea of how much data there is. And what we see here is a little bit of activity in the sound in the late 70s, early 80s. That was continental shelf oil and gas research for the most part, and then not much at all happening in the 80s. And then, hey presto, 1989, there was an oil spill. And since then, there's been quite a lot more concerted effort in looking at the sound. Now, looking at the data this way is kind of an analysis challenge because I'm basically taking data from everybody who will give it to me or wherever I can find it. So there's not a lot of controls on when it was taken during the year or where in the sound. I'm lumping it into those areas to deal with some of the differences in where. But dealing with it in terms of time is also tricky. So this is just a little example to illustrate that. So somebody goes out into Prince William Sound, say 3 times in a year, and they collect some CTD data. This is just temperature at 2 meters depth, so about my height below the surface. And this is just day of year from January to December. So they go out, they collect some data, great, wonderful. And then the next person comes along, they collect some more data. Maybe they collect at the same time as the other person, they may have some more elsewhere, and so on. Keep pushing the wrong button. And so it goes, and so you wind up with this big, messy data record from many different people taken at many different times. So it becomes kind of difficult to compare each individual data set. So you have to do a little bit of what I call numerical contortion to deal with this. And so what I do is I fit a line through it. And for the nerds in the audience, looking at you, Tom, there's an equation that goes with it. It's a cosine, so it just has an annual cycle and a semi-annual cycle. And it seems to fit the data pretty well. And go on back again. So we can go through this and use this model approach to take our data. So right here on the left is data, on the right is this modeling process. And again, here is the Central Sound, and here is the Northwest Sound. We can ignore the other stuff. So basically taking this big, messy, pretty variable data record and turning it into a kind of smooth annual composite. And so this is a composite of the annual cycle of temperature in, say, Central Prince William Sound. This is depth along the left here, and this is time of year along the bottom. And it's pretty much what you'd expect. During the winter, it's pretty cold. Everything's mixing quite well. The temperatures pretty similar from top to bottom. As we move into the spring, the sun comes out and things start warming up and we start seeing a warm layer form at the surface. That's again, this density effect happening. The heating of the water warms it up and makes it less dense and makes it tend to ride up on top of the cold water below it. And then as we move into autumn, the storms come back, there's a lot more mixing and a lot of that heat tends to dissipate down into the deeper part of the water column. You can see a little bit of change down at the bottom, which is deep water renewal. I can show that a little better in terms of salinity. Nope, wrong button. Here's the same thing, but with salinity. Again, central sound here, northwest sound here, surface near bottom, and it's pretty similar to temperature. Lots of mixing in the winter and the cold time. Into the summer, all of the melt of the snowpack and melting of glaciers increases the salinity near the surface, so these cool colors here, lower salinities, and it all tends to mix up down into autumn again. And then here in deeper water, you can see some higher salinity water coming in, and that's probably deep water being drawn in during the winter. Wrong button. Now, dealing with the data in this way is great, but to look at it over time, we need to sort of remove this seasonal cycle, because obviously the time that somebody goes out and makes an observation will partially determine what kind of observation they get. And so what we do is we basically subtract each point from this line and produce what we call an anomaly. Yes. And so all I've done is each of these points, I've subtracted it from this line. And so say this point here is about, say, 3 degrees cooler than the line. So that, instead of being 10 degrees, is 3 degrees cooler. And same is same for things that are warmer. So I've stuck with this color scheme throughout. Things that are red are generally warmer than average, and things that are blue are cooler. So here are the temperature anomalies for central Prince William Sound. And I've just shown a few of the depths. This is right near the surface here, 2 meters. This is 25 meters, 75 feet, 50 meters, 100 meters, and 200 meters. And so each of these bars is a quarterly anomaly. You can think of it as winter, spring, summer, and autumn. And then each of the little dots is actually a data point, so you can see how messy it is. And we're going from 1975 to this autumn along the bottom there in terms of time. Now this green line here, I've fit a trend line to it. So looking at the changes in these anomalies over time tells us how things are changing. If the slope of that line is positive, it means things are warming, and if the slope of that line is negative, it means that they're cooling over time. They're pretty small here. I have the actual slopes in here. Nothing really at the surface, but at every other depth, we're seeing a warming trend of about 1/5 to 1/6 of a degree per decade. So something on order of 1 degree Celsius over this entire data record. Now here is the same plot, but this is in Northwestern Prince William Sound. And it actually shows the opposite at the surface. We actually see a little bit of cooling at the surface. And down at depth, I'm sorry, you can't even read that. It's also generally warming. And if we look at the salinity as well, this is the salinity anomaly in Northwest Prince William Sound. We see a negative trend at the surface. So that means the water in the surface in the northwest part of the sound is actually getting fresher, which is presumably from all of that ice mass that is melting, as well as perhaps an increase in precipitation. We don't have a lot of data on that, unfortunately. And down at depth, we have a trend towards higher salinities, so not freshening, the opposite. And the explanation for that is probably to do with estuarine circulation. And it's again because of this tendency of water to want to form layers. And this is just a little cartoon of how that works. So, and this, the blue water here is fresh water that's coming from land, say glaciers, meltwater, rain, whatever. And then the green is salty ocean water. And so what's happening is the fresh water, when it comes into the ocean, it tends to float up on top and it moves out into the ocean. And while it's doing that, it's mixing with the salty water below it, but it's also dragging it along with it. And so as it drags the water, sorry, I'm going backwards here, as it drags the water with it to seaward, water from down deep actually upwells to replace it. And so if we think about our observation that it's getting cooler and fresher at the surface, obviously that means there's more fresh water coming in from land into the ocean. And then the increase in salinity in the deeper water is just ocean water getting sucked in after it and replacing it. Now to talk a little bit about the temperature trends, they are more driven by the atmosphere, most likely. These are a couple of fairly common climate indexes that you may have heard of before. The top one is the Pacific Decadal Oscillation. The official definition of that is it's the first mode of the empirical orthogonal function of the temperature field of the North Pacific Ocean. You can think about it as a very kludgy proxy of temperature. When it's positive, in general, the North Pacific is warm, and when it's negative, the North Pacific is hot. Northeast Pacific is kind of cool. And it obviously you can see changes over decades, 10s to 20 years. And then down below is the Southern Oscillation Index, and that is the difference between pressure between Tahiti and Darwin, Australia, which is not super sensible, but what you can think of it is an index for El Niños, which we are currently. And when the SOI is negative, that generally means El Niño type conditions, especially when it's really negative. So what we can do is compare this temperature or salinity record that I've made to these indexes to try and get a handle on how sort of the bigger picture is changing Prince William Sound. And so these are what are called lag correlations. Same pattern as before. This is the Central Sound here, and this is the Northwest Sound here. I'm sorry that they're kind of busy. There's a fair amount of programming that goes into these, and just taking two plots out is non-trivial. This is a lag along the bottom, and again, this is depth on the side. So right at the surface here, right near the bottom here. And so this is looking at how well Prince William Sound is connected to these larger climatic trends in the North Pacific. So at lag 0, that basically means temperature now compared to, say, PDO now. And at lag, say, 12 is temperature 12 months after PDO. So just looking at how connected things are. And this is a correlation, so it goes from 1, which means perfectly correlated. Temperature is, say, in lockstep with the PDO, or completely negative, which means temperature is doing the exact opposite. And so I've colored it here with this scale here. So basically anything green or yellow, you can safely ignore. It means it's weakly correlated. Things that are dark blue and into the reds are more interesting and stronger correlation between the sound and these bigger indexes. And you see what you probably expect in the sound at sort of shorter time scales. It's like half a year. It's correlating pretty well with this big North Pacific pattern. And over time, it actually stays that way with depth, and then not so much the surface, which is probably all surface oceanography happening. And this is basically the same pattern in the Northwestern Sound, a little bit weaker. The second panel here is salinity, and there's not really much of a trend that I I can see, which is not really something that you'd expect. And then looking at the SOI, this is again the El Nino index, and not seeing a super big correlation between El Nino conditions and Prince William Sound. And the effect of El Nino in Alaska is still kind of under discussion. There was a seminar I listened to last year by a meteorologist talking about El Nino events in Alaska, and it seems we get something different with each one. It can be warm and wet, warm and dry, cool and wet, cool and dry. And so same with the ocean. Not a huge relationship with El Nino. So of course, great. What does this mean for anybody? There's probably a beginner or two in the audience who will want to know about that. So I thought I'd talk a little bit about how the marine ecosystem works around here and what this might actually mean. And so this is just a dead simple idea of a food web. At the bottom here we have primary producers, otherwise known as plants. They have chlorophyll, so I colored them green. They're the movers and shakers. They take in nutrients, they use sunlight to photosynthesize and make more plants. And they are consumed by secondary producers, which are the plankton, krill, copepods, things like that. And of course, they're prey for higher trophic levels like fish and birds and whales and what have you. And so, knowing that there are trends in temperature and trends in salinity, they're going to affect the marine food web in different ways. Down at the bottom, there'll be some changes in nutrients due to stability, which is just another word for the tendency of water to form layers. And then, of course, temperature can affect basically any level of the food web. So I have a little cartoon here to show how that might work. I'll have to go back here to control it. So this is just sorry, I'm talking to the wall. This is a schematic of a little piece of ocean. So right here is our little piece of ocean. There's a surface layer, there's deep water. Blue dots are nutrients, green dots are phytoplankton. And so we start off in the winter, not much going on. But as spring comes, we get the sun shining on the surface layer. It strengthens that surface layer and kind of separates it from the deep water. And once it's deep enough that, or shallow enough rather, that phytoplankton are at the surface long enough to get sunlight, they will bloom, as we call it. They grow like crazy, and they use up all the nutrients in the surface water. So looking at our time series, that's what we see here. We see a little bloom in the phytoplankton, and then the nutrients disappear in the phytoplankton shortly thereafter because they don't have any more nutrients. And the zooplankton kind of track a little later. And then often in autumn, we see a little bloom. Again, as that stability breaks down, that can bring some more nutrients up to the surface, and the phytoplankton can make use of that last little bit of sunlight of the year. So I'll run that again. It happens kind of quickly. So what more heat in the ocean and more fresh water in the ocean means is we're going to see more stability. This layer is going to be stronger. It's the same as in my jar here. And there's different ways that can manifest. More heat can actually make it thinner. Out in the open Pacific, there's evidence that it's getting skinnier over time. And a thinner mixed layer means fewer nutrients available to phytoplankton, so presumably fewer phytoplankton during the spring bloom, or changes in how the blooms happen. And that, of course, is going to cascade up through the food web as things eat other things. The secondary producers themselves, we've been collecting them on our trips. We have it's basically a plant, it's called plant net. It's a windsock made out of mesh. And so we drag it through the water and rinse everything down into a jar and pickle it with formaldehyde, and Caitlin counts it in the lab. So we are watching what species we're seeing in the sound over time. And this is just for a single species. It's called Callus pacificus. It's a copepod. It's a little crustacean. This is time down the side here. So starting in autumn of 2009 and going up to this year. And we see some pretty big differences. These are all the different stations we hit. These four here are central Prince William Sound in the entrances, and then these ones are all various bays around the periphery. The location doesn't really matter. But what you can see is that you see different amounts of these species at different times. Callus pacificus is actually a pretty common warm water animal. It's more common down towards California. And I think we're seeing, yes, a bunch of them this last year. Caitlin? No?
Really?
Okay. I know there was some samples to go on this graph. And we're not really sure how this is going to change the food web, in that things that eat the plankton are going to be seeing different plankton to eat. And it presumably will change something. As well, whoop,
Any more species in show?
pardon?
Any more species in total?
No. No, I was mostly about temperature and salinity.
The neocolonists, what's happening to those?
It's all over the place. They're so episodic. I don't think we're sampling them super well. They're kind of a hit or miss.
And U1000s?
We see patterns in the Anomaly and the Facilia, because we capture them fairly well. With the adults, we simply don't capture them. They're too good a baby.
Wily coyote.
And then in the higher trophic levels, there's also like direct temperature effects. I was trying to find a picture that illustrates this, but I couldn't find one. But it's kind of a general rule with cold-blooded animals that when it's warmer, their body size tends to be a little bit smaller. I heard a lot about small salmon on the flats this year swimming through nets and such, which is consistent with a warmer ocean. And this is a pretty general rule for all cold-blooded animals, so it will presumably impact the plankton as well as fish and higher trophic levels. Oh, wrong button every time. Sorry. Now, of course, that was a vast oversimplification of what the food web actually looks like. This is a slightly closer representation. The details aren't very important. I just wanted to show that it's really complicated. There's a lot of moving pieces in the ecosystem in just Prince William Sound. Not to say in Alaska or the ocean in general. So anybody who tells you that they know what's going to happen, I would take it with a grain of salt.
So do those circles represent the quantities?
Yes.
Specifically?
Yeah, this is in the same sort of order as my little fake model. So this is trophic level 1, which is plants, trophic level 2, things that eat plants, and so on. So all down here are phytoplankton and plants, a little bit of detritus. These are all what we call grazers, and then we start getting up into things that eat plankton, various fish, and then incivorous fish, things we like to catch up here. Just to illustrate how everything is eating everything else. And so making predictions is really difficult. And I thought I'd end up just with a little talk of what might be happening after I just said that human beings are really terrible at making predictions. NOAA runs a climate model, and you can just download the results. So this is a map of the projected sea surface anomalies for basically the world, but I imagine you're probably mostly interested in the North Pacific. So this is their December, January, February prediction, and there's our blob in the North Pacific. And what? There's the January, February, March, perhaps a bit smaller. Also possibly a cold anomaly a little bit to the south. There's February, March, April. A little more of the same. March, April, May, more still. Obviously a lot can happen, but the projection for the next half year or so is probably continued warm. Obviously we have a really big El Nino brewing right now as well, and everyone's watching that really closely to see what happens with that. And that's all I have for you.
So Godzilla, El Nino might not displace the blob?
It's keeping people busy talking about it. There's actually a blog. I don't know if you found that.
I think I'm referring to the blog by the meteorologist that you shared or Caitlin shared or somebody.
Yeah, their latest post was showing something similar to this, slightly different model, but saying the blob ain't dead yet. Generally, like I said, with an El Nino, it's really hard to predict what's going to happen in Alaska. But in general, when this is actually El Nino, right here at the equator. It's for those of you who don't know, when El Nino happens, this big pool of water is normally over on the other side of the Pacific. And for reasons we don't really understand that well, sometimes the winds that hold them there die off. And so this entire slug of water just comes right across the Pacific and runs into South America. And when it does that, it usually travels down and up the coasts in either direction. And so sometimes for Alaska it means warmer weather. So we could be seeing an El Nino signal travel all the way up here and enhance the blob. Hard to know. I just read something else today saying, well, often after really strong El Nino, we have a La Nina, which is kind of the opposite of El Nino, which means cooler conditions. So maybe it could be flipping in the next year or two. But as I said, we're terrible at predicting, so don't bet on it.
Don't sell your skis yet.
Rob, speaking of skis, could you go back to the December, January, February? So,
It's
closer to sell your skis.
yeah, it's still warmer out there. As of September 27th, when we were last out there, it was about 1.5 degrees Celsius warmer than average. And once it's nice, we're going to do one more trip and check it again. But I expect it'll still be warmer than average. For skiing, anything could happen. We could get that polar vortex. Yeah, the polar front, if it dips down on us instead of Hokkaido like it did last year, we could easily have another snowpocalypse. Warm temperatures also mean a lot more moisture in the atmosphere.
let's not.
We broke everything.
Maybe half a snowpocalypse?
Yeah, I don't need the drama, I just need to.
No.
What's the water temperature now in the south?
Say 1.5 degrees Celsius warmer than average. Or you mean the actual?
Yeah, what's the number?
I couldn't tell you off the top of my head.
45 at the buoy,
Okay.
7 Celsius or something recently.
Yeah.
Yeah.
Yeah. It's funny, you start working with anomalies and you don't even know what the actual temperature
Real
is.
world.
You just know it's warmer than average.
Great, well, thanks again.